Hello, this is Chad Davies. Before I begin the podcast, I have a brief bit of housekeeping, or maybe I should say podcast keeping, whatever. Over the last week, due to some fantastic publicity on some of the chemistry and physics education listservers, the podcast has picked up about 150 new listeners. To those who have just arrived, welcome. Glad you have decided to join us on our odyssey. If you're wondering what this is all about, I would encourage you to go out and download and listen to Episode 0, Setting Out, as I lay out some of the goals of the podcast there. You may also want to give a listen to our first series on Science as Inquiry, if a broad overview of my view on what science is and how it works might interest you. For my listeners who have been around for a while, we're about to roll over 5,000 downloads for the podcast, and I'd like to say thanks for your being here and taking the time to hear and consider my ideas. For some podcasts, that's really small potatoes, but I'm really humbled that so many of you take the time to listen to my ramblings. If you have a moment, I'd like to suggest a few ways in which you can engage a bit more fully in what we're doing here. First, go to the podcast website at thescientificodyssey, all one word, .typepad.com and leave a comment or ask a question. Seriously. I want to make sure the comments thing on the site work. And I'd also really love to hear from you. Tell me what has piqued your interest, or something you might have learned, or something I might have left out. Let me know how I'm doing, or how I can get better. At the end of the History of the Atom series, assuming we ever get to the end of the History of the Atom series, I'd like to do a Q&A show, so post some questions for me. I'll collect them and see if I can get some good answers for you. Second, it would be a huge help if you could leave a review for the podcast on whatever service you're using to get it, if the service allows you to do that. If you don't want to write anything, that's fine, but take a moment to click whatever number of stars or thumbs up or whatever the site might have. One of the things I'm hoping to do with this project is to show more people how science is actually done, and reviews help get the podcast noticed. Third, and finally, if you run across a cool science story or a website that you think that does a good job of presenting information about science and how it's done, feel free to post a link on the podcast's Facebook page. You can search in Facebook using the show's title, and it'll be easy to find. I can only spend so much time searching for interesting stuff, and my background probably makes me a bit blind to good research done in many fields, so help me out if you can. Okay, with all that said, let's get on with the podcast. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 2, A History of the Atom. Episode 9, The Physical Atom. Over the last few weeks, I've looked at evidence for an atomic picture from the perspective of the emerging science of chemistry, beginning with pneumatic chemistry in the mid-1700s and culminating with Arrhenius's ionic theory in the last decade of the 1800s. The 150-year development of the subject had been anchored by Dalton's atomic theory, which, by the end of the 19th century, was a well-accepted scientific idea. It would be a mistake, however, to suggest that all of the evidence in support of atoms came from the investigations of the chemists. Working in parallel with the masters of the crucible and flask were the physicists, and it was their attempts to understand and explain some of the basic mechanics of the same systems being studied by the chemists that provided the physical evidence that complemented the chemical research being done. In a sense, it was the physicists, at least those who followed in the footsteps of Galileo and Newton, who were the first to advocate an atomic view of matter. Both of those men had assumed the existence of very small particles as the fundamental building blocks of matter, though neither of them produced much empirical evidence in support of that view. In both cases, the atom just seemed to make more sense than matter being continuously distributed, and so that's the default idea they both went with. Their arguments were much more philosophical than scientific, and their explanations of first motion and then force didn't require that matter be either corpuscular or continuous, as they dealt with objects as idealized point masses in their treatments first of kinematics and then later dynamics. In the last half of the 17th century, several natural philosophers, working from the assumption of Newton, attempted to determine the size of atoms using physical means. Generally, they arrived at numbers on the order of 1 micron or a micrometer, which is 1/1000th of a millimeter, the smallest division one usually finds on a meter stick. While these numbers are still about 10,000 times too big, they do represent the first good attempts to determine the atom size with any real accuracy. The first effort to create a physical argument using an inherently atomic model came from a man by the name of Daniel Bernoulli. Bernoulli was attempting to understand a specific law related to the behavior of gases. In the United States and Britain, the law is known as Boyle's law, and it describes the physical relationship between the volume a gas fills and the pressure that gas exerts on the walls of the container that defines the volumes. What the law says is that the two variables are inversely related to each other when the temperature of the system is held to be a constant. In other words, if the volume of the container is decreased, then the pressure the gas exerts on the walls of the container will increase. While Boyle didn't discover this law, he was the first one to report it to a broad audience in England, and so he's generally credited with its discovery, at least there. The actual credit should go to Richard Tanley and Henry Power, who both discovered the relationship independently of each other and prior to Boyle's report. Now, leaving issues of credit aside, at least in terms of the discovery, what Bernoulli was curious about was why did the relationship exist in the way that it did? For us now, accustomed to an atomic model, perhaps the answer might seem a little obvious, though I would argue it's not as obvious as one might think, but at the time it wasn't nearly as clear. In his 1738 work, Hydronitamics, Bernoulli was able to mathematically derive Boyle's law by making a couple of assumptions. The first was that matter was composed of atoms moving in a void. Back to that again. The second was that the pressure was just the average force exerted on the walls of the container by the atoms colliding with it. The third was that heat was actually the mechanical energy of the atoms moving through space, what Newton had called energy of motion. By assuming that the gases were made up of a very large number of single atoms of the same type, he was able to mathematically derive the correct relationship between the pressure and the volume of a gas. So, the question probably arises at this point, why wasn't the atomic idea adopted on physical grounds some 80 years before the work of Dalton? I mean, Bernoulli had just kind of proved that it explained something. Well, there are two reasons. The first was that the numbers of atoms suggested by Bernoulli's work and the unobservably small size of those atoms seemed more than just a bit mind-boggling to many. It wasn't until chemists were able to define what we now call the mole and the quantity of atoms that would represent that scientists would begin to come to grips with the truly vast number of atoms even in the smallest sample or quantity of gas. Second, and more importantly, there were a number of physical phenomena that would be described very successfully by continuous models of matter within just a few decades of Bernoulli's work. For example, as we've discussed in previous episodes, good research was being done on chemical phenomena beginning around the time of Bernoulli's work, and by 1760, the prevailing model became that electricity was actually some sort of electrical fluid that moved through a conducting medium, much like water would flow through a hose. The biggest argument amongst the investigators of electricity, therefore, was whether there were two fluids going in opposite directions or just one fluid in one direction. Benjamin Franklin was able to successfully argue for the latter model, which is the mental idea many of us have today. Franklin's single fluid model of electrical current was very successful at describing the behavior of most simple electrical circuits, and so it became the accepted picture of electricity for over 100 years. So pervasive is this idea that we still use fluid terminology to describe electricity. We describe electrical quote-unquote current as quote-unquote flowing through a wire, a model that's entirely fluid in its nature and language. This in spite of the fact that we now know that electrical current in a metallic conductor consists of a very large number of moving, electrically charged particles that we call electrons, and that those electrons are traveling through the conductor, albeit at a surprisingly slow speed. In another example, the great mathematician and physicist Euler had been able to describe all of what we now call hydrodynamics, which is the physics of fluid flow, using mathematical methods that assumed matter was continuous. The strength of this approach was that one didn't have to have some sort of an assumption of atoms, which prior to 1800 had very little empirical support. In fact, Bernoulli's own book, where he makes that derivation of Boyle's law using what is now called kinetic theory, was actually mostly a discussion of the various laws of fluid flow in a number of contexts. It was quite successful in representing laws governing the motion of fluids using a description of matter that was continuous. So, even if Bernoulli thought matter was atomic in nature, those who read his best work found much evidence to support a non-atomic picture. What this all gets at is a split in the metaphysical approach to understanding nature that had developed in physics by this time. Best encapsulated in the work of Kant, there is a very clear distinction between the mechanists who used mechanical explanations of phenomena that depended on particles and forces, and the dynamicists that eschewed the unnecessary entities such as atoms or molecules and relied only on the moving forces of attraction and repulsion. While those who adhered to the dynamical approach to natural philosophy did not completely reject atoms as such, they did reject the idea of atoms in a void. This dichotomy is clearly seen in the distinction between the hard, spherical, massy atoms of Dalton, who was clearly influenced by the mechanistic approach of Newton, and the point atom monads of Boscovich that were only thought to be centers of force. While this distinction might seem trivial, the former atom moved through a void, while the latter was part of a continuous description of matter that allowed for no void whatsoever. Many of the scientists of the 1800s, including both Davy and Faraday, will find Boscovich's atom much more compelling than that of Dalton. While Davy was generally skeptical of atoms, saying in 1812 that atoms were, quote, mere creatures of imagination, unquote, he would eventually be persuaded by their existence by the chemical evidence we've already discussed. His student Faraday would not accept an atomic theory until 1844, when it became fairly clear that his descriptions of electrostatic and electrodynamic processes required there to be point charges. Because the Boscovich atom could better account for the physical attributes of crystalline structure and electrical conductivity than Dalton's atom did, Faraday eventually embraced that description. While this may seem like a bit of a tangent now, it will become important once the quest to understand the structure of the atom enters the 20th century. The area of research in physics that ended up lending the most support to an atomic theory of matter was that of first thermodynamics and later what was known as statistical mechanics. Prior to about 1780, the dominant idea regarding heat was that it was caused by the motion of small particles, much like what had been described by Bernoulli. Evidence that heat was actually a product of motion could be found in the arguments such as rubbing two bodies together in such a way that it produces heat from the motion. However, between the years of about 1780 and 1825, there arose the hypothesis that heat was actually a fluid that could be transferred from a hot system to a cooler one. This fluid, called caloric, was undetectable directly, which led to it being called an imponderable fluid in the terminology of the time. However, the effects of its transfer could be measured by taking the temperature of the system. The foundations of the idea of a caloric fluid originate in the researches of a man we've already discussed in relation to pneumatic chemistry, Dr. Joseph Black. In considering how objects heat up and cool down, as well as how they melt, Black came up with the ideas of both specific and latent heat in 1757. Specific heat has to do with how much heat is required to raise the temperature of an amount of a substance by a certain amount, say 1 degree. To use Black's example, water has a greater specific heat than mercury, because it takes more heat to raise the temperature of 1 gram of water 1 degree than it does to raise the temperature of 1 gram of mercury. Latent heat, on the other hand, has to do with the observed fact that one has to add a certain amount of heat to a given amount of substance to get that substance to melt. While this heat is being added, the temperature of the substance doesn't change. The example here is to think about melting an ice cube. In order to melt an ice cube, one has to continue adding heat to change the ice into water. While this process, called a phase change, is taking place, the temperature of the ice and water mixture remains at exactly 0 degrees Celsius, or in old units, 32 degrees Fahrenheit. The added heat doesn't go into raising the temperature, but into changing the phase of the substance from solid to liquid. These observations seem to be incompatible with the more dynamical model of the time, and given the general tendency of the time to want to explain things in terms of fluids, heat was soon being described in that fashion. Both Lavoisier and Dalton would promote the caloric theory of heat, as would another great mathematician and physicist, Pierre-Simon Laplace. In fact, according to Robert Purington, it is only after Laplace's death that the influence of the caloric hypothesis of heat begins to fade. While I will have to leave a detailed history of the development of both thermodynamics and statistical mechanics to another time, I will try to hit the high points of the parts of the development of both that are germane to our story. Thermodynamics is a field of physics born out of the attempts to understand what was going on in the steam engine to produce work. In fact, it's been said that science owes more to the steam engine than the steam engine owes to science. In trying to understand how heat drove the steam engine to do the work that it did, all of the basic principles of thermodynamics, aside from specific and latent heat as previously discussed, were discovered. The first good experimental refutations of the caloric theory of heat came from the work of Benjamin Thompson, also known as Count Rumford, and Humphrey Davy. Thompson, among many other things, was involved in the making of cannons for the government of Bavaria. Making a cannon at the time involved using a drill to bore a hole in a solid piece of metal. As you can imagine, this process generated a lot of heat. If that heat was a fluid, there should be a point where it would run out or all get transferred out of the system into something else. So what Thompson did was perform the process of boring the cannon out immersed in a water bath. What he found was that he could heat up as much water as he wanted by just continuing to drill in the metal of the cannon. In other words, the process never stopped generating heat as long as the drilling continued. This meant that there wasn't a fluid being transferred, but rather that the motion of the drill against the metal of the cannon was producing the heat. Now, Thompson had already received the prestigious Copley Medal from Britain's Royal Society for his work in conduction and insulation, and when he read this paper on heat in 1798, it cemented his scientific legacy. A year later, he would take the lead in founding the previously discussed Royal Institution, which would hire both Thomas Young and Humphrey Davy. Davy would have written a number of papers prior to joining the Royal Institution on the melting of ice by friction that would mirror Thomson's work. Thomas Young would show that light was a wave, and in doing so, set in motion a number of arguments suggesting that heat would be better described by a wave phenomenon rather than as a fluid. While this idea was fairly quickly discarded, it served as a nice transition hypothesis from the caloric model of heat back to a dynamical description. This transition was accomplished once it was understood that there was a fundamental difference between radiant heat, which was actually shown to be another form of light unseen by the human eye, and the heat energy that was involved in running the steam engine. As an additional note, in 1815, Young attempted to measure the size of the molecules that make up water by making observations of what was known as capillary action. His measurements gave him a number that was within a factor of 10 of the actual value. Beginning in about 1820, just as the appeal of the caloric hypothesis was beginning to fade, a British physicist by the name of John Herapath once again took up the kinetic approach first pioneered by Bernoulli. His work assumed that gases were made up of particles that were infinitely hard and that lost no energy or momentum when they collided either with each other or with the walls of a container. However, since during this time the existence of atoms was still a matter of some serious debate, as was their nature if they did in fact exist, Herapath's work received little acceptance due to his associating the temperature of the gas with the momentum of the particles rather than with their kinetic energy. Nevertheless, this explanation would lay the foundation for the development of what is now known as statistical mechanics. Herapath would publish a revised version of his work in kinetic theory in book form in 1847. His work from the 1820s onward would influence a number of British physicists, most notably John James Waterston and James Joule. Waterston was a relatively unknown physicist who took up the problem of gas laws in the early 1840s. Working with what was initially a wave theory of heat, and later with a more truly kinetic theory, he was able to derive a number of correct expressions for the behavior of gases beyond that of Boyle's law by correctly assuming that the temperature of the gas was dependent on the square of the atom's speed rather than just on it directly, as Herapath had done. Unfortunately, his work was received even more poorly than Herapath's, and it was quickly forgotten except by William Rankine and Hermann von Helmholtz. These two men are likely responsible for showing Waterston's work to August Kronig, who reworked the ideas in 1851 into a stronger, more complete, and more understandable theory that was better accepted in Europe. James Joule was already well known for his work in showing that heat was equivalent to mechanical energy, and in 1848 he presented a paper to the British Association for the Advancement of Sciences that laid out his version of a kinetic theory that was once again founded on the idea that gases were made up of either atoms or molecules. Correctly understanding that temperature was related to the energy of motion of the particles, Joule was able to calculate the specific heats of several gases and the speed of hydrogen atoms at 60 degrees Fahrenheit. The success of this presentation, combined with Joule's stature in the field of thermodynamics, strongly pushed the focus of research away from using any sort of caloric or wave hypothesis towards a kinetic description that assumed the existence of atoms. While these descriptions of the behavior of gases worked in special cases, most notably gases that would obey what we now call the ideal gas law, they did not generally work for all gases. There were still a number of different gases, most notably ammonia, which could not be explained by the kinetic theories of Joule or Kronig. This deficiency would be corrected in three papers published between 1857 and 1871. The first of these was published by Rudolph Clausius. What Clausius recognized was that if particles of a gas were, in fact, molecules, they would be able to store energy not just by moving, what we now call translational energy, but also by vibrating and rotating. Now, like Joule had been, Clausius was already well known for his work in thermodynamics, in which he had developed a formulation of the first law of thermodynamics, which sort of created the idea in good, solid form of conservation of energy. Publishing his revision of Kronig's kinetic theory in 1857, Clausius made great progress to extending the work to non-ideal gases. It should be noted that Clausius claimed that his formation of the kinetic theory was done independently of Kronig's, but it hardly seems likely that he was not at least aware of that work, as it was well known throughout Europe at the time. Clausius's paper then spurred Scottish physicist James Clerk Maxwell to recognize that not every particle of a gas would actually be moving at the same speed. By assuming that the speeds would be distributed around an average, Maxwell was able to expand Clausius's work in such a way as to be applicable to all gases. Maxwell would extend and refine this work through 1866, with applications not only to physics related to the behavior of gases, but back into a number of thermodynamic concepts, thus moving that field solidly in the direction of being built on an atomic foundation as opposed to one that had been rooted in wave theory, which of course, as we talked about earlier, had replaced the even earlier caloric hypothesis. Finally, in 1871, Ludwig Boltzmann extended and generalized the work of Maxwell in order to take into account the effects of gravity on the behavior of a gas, ideal or otherwise. Over the course of the next several years, Boltzmann would fully integrate the idea that molecular motions were statistical into both kinetic theory and thermodynamics, and he would be the first to recognize that entropy was a measurement of the disorder of a system. This statistical approach would allow Einstein, in 1905, to derive the equations of Brownian motion as they applied to molecular objects, and that would become the strongest empirical proof for the existence of atoms. The work of Clausius, Maxwell, and Boltzmann also made it possible to calculate the diameters of atoms, and in doing so, provided the physical evidence to support the chemical evidence that had developed from the period of 1830 to 1870. In this parallel development, however, there are some cogent points that should be noted. The first is that it would be a mistake, I think, to consider the physical atom and the chemical atom as being the same thing. As Maxwell would say in an address to the British Association to the Advancement of Science, quote, "The definition of the word molecule, as employed by the statement of Gay-Lussac's law, is by no means identical with the definition of the same word as in the kinetic theory of gases. The chemists ascertain by experiment the ratios of the different masses of different substances in a compound. From these, they deduce the chemical equivalence of the different substances, that of a different substance, say hydrogen, being taken as unity. The only evidence why substances combine in definite ratios is that the molecules of the substance are in the ratio of their chemical equivalents. And what was called combination is an action which takes place by a union of a molecule of one substance with the molecule of another. This kind of reasoning, when presented in proper form and sustained by proper evidence, has a high degree of cogency. But it is purely chemical reasoning. It is not dynamical reasoning. It is founded on the chemical experience, not on the laws of motion." Unquote. This distinction between a chemical atom and a physical one would be one made by physicists from 1840 onwards. We know now, of course, that they are one and the same, but that wasn't nearly so clear at the time, and those who held it were making a pretty big assumption given the evidence available. Second, as I've already noted, the picture of the chemical atom as solid, hard, and massy wasn't typically shared by many physicists. For a variety of reasons, physicists were drawn more often to Boscovich's monad atom, or, as was the case with Maxwell later, an atom that consisted of some sort of a vortex. The Daltonian atom presented a number of physical difficulties in the types of problem physicists were considering at the time, most especially in electrodynamics, and thus a number of physicists would hold the idea of an atomic theory at arm's length for quite some time. William Thompson, for example, the man who would later become Lord Kelvin for his brilliant works in thermodynamics and energy, would not accept the existence of atoms until the 1860s, and only in the vortex model from the work of Helmholtz and Maxwell. Wilhelm Oswald, whom we discussed last week in relation to electrochemistry, wouldn't accept the reality of atoms until 1909. However, given the evidence, both chemical and physical, it was fairly clear by 1880 that matter was atomic in nature, even if the exact model was still being disputed. It is at this time that certain technologies will become available that will allow physicists to probe the structure of matter more deeply. Alongside that, a pair of chemists, husband and wife, will begin looking at elements that have the peculiar property of being able to expose photographic plates simply by touching them. The accumulation of evidence from these two seemingly disparate tracks will lead to a revolution in the understanding of matter, and it is that revolution we will consider in our next episode, the divided atom. So until then, full sails on your journey.